Hello, everybody. We have a couple of more problems or examples that we will solve now on the linear momentum equation. So one of them is this example here where we have water flowing out of the nozzle. So this is the nozzle that the water is coming out from. It has an average speed of 20 meters per second. So this is the velocity of this water nozzle or the water from this nozzle, and it strikes a stationary vertical plate. So the water is hitting this plate at a rate of 10 kilograms per second. This is the mass flow rate, and after the strike the water stream splatters off all directions. So the water, of course, is not going to penetrate this metal plate. It's going to splatter from from all directions. So it's going to be like a circular spreading of the water in all angles. We just see the flow up and down because this is the side view. We want to determine the force needed to prevent the plate from moving horizontally. So this plate, of course, this water is making or applying force on this plate. So for this plate to stay in its place, there is a reaction force that is acting on the other direction. So we want to know how much force is needed to prevent the plate from moving horizontally, and we assume steady flow, and beta is equal to 1, which is the correction factor. So again, the first thing we need to do is to define the control volume, and in this case the control volume is this red dot dashed line, the reason we chose it because we need a control volume that has the reaction force. So this will include the reaction force, and also we know the inlet velocity. So this makes the calculations easier. So we need to determine the force that prevents the plate from moving horizontally. So we are interested in the horizontal reaction force, okay, which is this. So we will write the equation only in the x direction, and by writing the equation in x direction, we have the velocity at the inlet is 20 meters per second. This is what was defined here, and the exit velocity is all in the z direction or in the y direction, which is in and out of the screen. So there is no velocity exit velocity in the x direction. That's why u2x is 0. Okay. Now we can and also for the pressure, we know that if we want to analyze the forces, again we said the forces are body forces, and here the gravity is ignored. We don't have any gravitational force here. For the surface forces, we have the reaction force, which is this. We have the viscous forces, which is not going to be included because there is no viscous forces on this red dotted line, and we have the pressure, and all this system in the control volume is under atmospheric pressure. So as we do all the time, we apply the gauge pressure, and that's why all the pressure or the pressure acting on all the parts of this control volume is atmospheric pressure, so the gauge pressure is 0. So the equation will end up to be the summation of forces in x direction is 10 times 0, which is the exit velocity. There is no exit velocity in x direction, minus 1 times 20, so it's negative 200 newtons. And the force that we have is the reaction force in the negative x direction, so it's negative Fr, so Fr is 200 newtons. So it's a simple problem. Of course, we didn't include the velocity and the exit because it's not in x direction. So if we write the equation in the y direction or the z direction, this velocities would be included. Okay, we have one more problem here where water flows at a rate of 18.5 gallons per minute through a flanged faucet. So this is a flanged faucet. Flanged means that it has a flange, like a some part of the faucet that has holes, so that the nuts or the bolts can go through this and fix it to the wall or whatever the thing that is fitted to. We know the inner diameter of the pipe is 0.78 inch, which is 0.065 feet, and the pressure at the location is measured to be here. The pressure here is 13 psi gauge, so this is the gauge pressure. We know the total weight of the faucet and the water inside it is 12.8 pound force. It's the weight, it's already calculated, it's not the mass. So we need to see how much force is on the flange or on the bolts. There is a reaction force that is keeping the faucet from, or keeping the faucet in place. So the first thing is this reaction force, it's not given, it's just an assumed direction. So we don't know what is the actual direction of the reaction force, so we assume direction, and then if it's positive, then the assumption is right. If it's negative, then it's the opposite direction. But first we need to pick the control volume, and this is, if you remember, this is a figure that we saw before when we talked about the choice of control volume, and we discussed before why we will pick this control volume, because it will make the forces that we include much simpler than if we include the water or the region or the volume inside the faucet. So so by analyzing this control volume, we have this is gauge pressure, this is atmospheric pressure, and of course this whole system is under atmospheric pressure, so this is the only surface force that we include. So again, let's start with I just did some conversion for the units to unify all the units. So this flow rate was 18 gallons per minute. I converted it into foot cubes per second. And we calculated the mass flow rate because we will need it. The diameter, I converted the diameter, it's already given in foot, and I calculated the area in foot square, and the velocity here and here are equal, and it's 12.42 foot per second. So it seems like a trivial step, but it's very important. It's very, very important to make sure that the units are adjusted beforehand, because if you don't do this, it's very probable that you will forget about this later, and you can use the wrong number later. Anyway, so this reaction has two components, in x and in z direction. So we'll write the equation in x direction first. So for the forces, we have no body forces because these are acting in z direction. So we have the pressure force, which is P1 gauge times the area, which we calculated here, this area, and we have also the reaction force. We don't have any viscous forces, and of course we don't have any gravitational force. So this is the equation. The summation of forces is m times beta 2 u2x minus beta 1 u1x. So the P1 gauge times A, so this is the pressure force, and this is the reaction force. Of course, the reaction force in z direction is positive because the assumed reaction force is in positive x direction. So this is just substitution. This is the mass flow rate. This is for the velocity. We have the velocity here. It's already known to be what we calculated here, 12.42 foot per second. But we don't have any exit velocity in the x direction. This is in the z direction. So the exit velocity is 0. That's why we put it as 0, and we put it as 12.42. And here we did this conversion factor because this pressure is in pound force per square inch. So this is pound force, and this of course will be pound force. So what we have here is pound mass foot per second square. So we multiply it by 1/32.2 to convert from pound mass foot per second square to pound force. And this is an important thing that you need to pay attention to when using the US units. It's important. So you need to pay attention to this. So by doing the math, you will find that the force, the reaction force in x direction is negative 7.2 pound force. So it is acting in this direction, in the negative x direction. The same for z direction. If we write the equation, the forces that we have, it's the gravitational force and the reaction force. There is no pressure force here, and there is no inlet velocity because it's all in x direction. So this is in negative z direction. So the velocity here is negative 12.42. So the reaction force minus, of course, the reaction force is positive because it's acting, the component is acting upward, and the gravity is in negative direction. So this is the weight. Of course, the mass flow rate is the same, multiplied by 1 times negative 12.22 because it's acting downwards, and the same convergent factor. So we find that the reaction force is 11.8 pound force. So finally, we can write the equation or the force like this, that it is acting in the negative x direction by 7.12 pound force, and in the positive z direction with 18.8 pound force. Okay, so yeah, that's it. So you'd see that all the problems that we solve are just using the same equation. It's only the matter of analyzing the forces and knowing how to calculate the velocities properly and what velocities to include in each case. We have one last problem here. We have a firefighter. He is holding a nozzle and he is extinguishing a fire, and the exit diameter is 8 centimeter and the flow rate is 12 meter cube per minute. And we want to calculate the average water velocity at the exit and the horizontal resistance force by the firefighter to hold the nozzle. So for the first part, it's simple. The velocity is the volumetric flow rate divided by the area. So we have the volumetric flow rate. I converted this into meter cubes per second, and for the velocity, it's going to be the volumetric flow rate divided by the area. We already know the diameter, so we calculated the velocity. For the second part, to calculate, we are interested here in the horizontal resistance. So for the horizontal resistance, we'll need the mass flow rate, which is easy to calculate. We know the volumetric flow rate, multiply by the density, we get the mass flow rate. And by applying the momentum equation in x direction, this is the equation: summation of forces in x direction is beta m2 u to x minus beta m1 u1x. And let's first set our control volume. So the control volume that we will pick is this, because this will include the reaction force acting on here, and this is the velocity that we already calculated in part A, so we know the velocity. So from this we can put the forces that we have. We have the let's say this is the horizontal direction is x direction and vertical is z, and there is a pressure inside the pipe with a velocity, and there is a reaction force. I'm assuming it's going to be in the positive x direction. And we know the velocity here. So if we write the equation, there is no velocity or feed velocity in the x direction. The feed is in z direction. So this is u1x is 0. So we have u2x only. And for the forces acting here, there is no gravitational force in the horizontal direction. There is no pressure forces because all the system we have here is under atmospheric pressure. There is no viscous forces, so it's going to be only the reaction force, and it's going to be the reaction force is the mass flow rate times the mass flow rate times this is the mass flow rate, this is the correction factor, times the velocity minus 0, because this term is 0, so it's 7,958 newtons. So this is the last problem that we will solve here, and I hope this is makes the problems makes the calculations clear, and by this we end chapter 6, and inshallah next video we'll start with the next chapter, inshallah. So I'll see you then, inshallah.